If we start looking at the cerebral white matter, we're looking at more myelinated neurons compared to unmyelinated neurons. Now, this is going to be all the different tracts that are myelinated inside of the brain. It's allowing communication between different areas of the cerebrum, as well as the central nervous system up and down the spinal cord. So all this cerebral white matter is running throughout the brain, but in different directions, different patterns. We have what's called commissures. Now, commissures are corresponding between the two hemispheres. That means the commissures are going right to left, left to right. Commissures. The largest of these is called the corpus callosum. The corpus callosum is this very large commissure that connects the right and left hemispheres. We have association fibers. Now, these association fibers are connecting the same hemisphere. That means they're connecting from the anterior to the middle, or the middle to the posterior. But they're staying within the right or within the left. They're not going across. So these are going to be association fibers. So commissural, across, association are within. Then we have projection fibers. Projection fibers are projecting from the brain out. They're going to be taking information from the brain, heading down the brainstem, down the spinal cord. So projection fibers are leaving the brain and then coming into the brain. So it's connecting the body's receptors and effectors, basically putting all the pieces together. These are the projection fibers. So if we look at this image, we'll notice that we have these kind of loops that are being formed. Those loops are all going to be the association fibers. They're all within the same hemisphere. But then notice the projection fibers. Those are the lines all heading down to the thalamus. They're projecting out of the brain. And then you have the green dots here. Those green dots are symbolic because they're going across. They're connecting. So that's the corpus callosum, for example, the commissural fibers. So 3 different directions of fibers. Association within the same hemisphere. Then you have projection, leaving the brain and coming in. And commissural, connecting right and left halves. Let's jump into the basal nuclei. Now, the basal nuclei is actually made up of several different structures. It's this area right down here. What you're seeing here is you have the caudate, you have the putnam, as well as the globulus pallidus. All 3 of those parts together are making up the basal nuclei. So it's very deep within the white matter. It's kind of really right in the middle center of your brain. Now, the functionality of the basal nuclei. First off, motor control. It's helping to coordinate and control your motor movements. It's looking at the learned and patterned movements again. How you're moving, how things are going. It's meant to also, this is the really important part, inhibit antagonistic movements. What it's trying to do is trying to stop unnecessary movements, ones that would counteract what you're doing. So for example, if you're trying to reach to grab a glass of water, would it be very useful for your arm to also go to the side or to pull back? Those would be antagonistic movements, unnecessary movements. It's trying to be a nice, smooth movement in, preventing random other movements that would prevent you from completing the action. So this is the basal nuclei, trying to get rid of unnecessary or antagonistic movements. So it's looking at movements of the body in general, but also removing antagonistic ones, removing unnecessary movements. So a little bit about pathology with the basal nuclei. Huntington's disease. In the case of Huntington's disease, we're actually a buildup of a mutant protein. Not get into what the protein is, don't worry. But there's this mutant protein that's building up. It ends up breaking down the basal nuclei. So as the basal nuclei is being broken down, that means you're not able to prevent these antagonistic, these unnecessary movements. Your movements become more jerky, more rapid. They're not really doing what you want them to do. So it's causing problems with your fluidity of your movements because you have now these antagonistic, these unnecessary movements occurring. as the basal nuclei breaks down. It's not able to prevent them anymore. So the idea of Huntington's disease. Another one is ballism. In the case of ballism, a lot of times involuntary and often violent jerky movements. So very quick and sudden movements that you didn't want to happen. Things that you weren't thinking about, that you didn't want. And this is due to damage to the basal nuclei. So again, the basal nuclei being damaged, it can't function properly. It can't prevent those antagonistic or those unnecessary movements. Tardive dyskinesia. Now in this case, its problem is long-term usage of dopamine antagonists. So if you're trying to basically reduce dopamine, so usually antipsychotics in this case, now the body itself is having these more repetitive, involuntary, pretty much purposeless movements. The body just needs to move. The body has to stay in motion. So you just be sitting there, all of a sudden the arm just starts moving around. You just feel the need to move. You're having a difficulty not moving. And it's all because the dopamine levels were thrown off, and therefore the whole system just didn't quite work right afterwards. So tardive dyskinesia. All right, let's move into the limbic system. We mentioned it already in a previous bit about being the emotional center of the brain, which it is. The limbic system is your emotional brain. It's what puts your emotions and feelings together. It helps you respond to odors, to visual cues, to sensory input. Think about it this way. If you smell a particular cookie baking, maybe you might associate that with a particular relative baking cookies or a bakery. Or if you see a particular item, you might associate that with a person. This is the limbic system, putting emotions to different visual, auditory, olfactory, to whatever cues you have. And it's helping to interact with the prefrontal lobe. We mentioned this before. So yes, the limbic system is by itself, but it integrates with the prefrontal lobe. It's going to give you a relationship between feelings and thoughts. That's why certain thoughts will elicit a certain feeling in your body, elicit a certain reaction. And it allows you to kind of emotionally react to conscious understandings. What that means is you realize something's occurring and your emotions then can kick in based on what you're realizing is occurring. So it's putting emotions to what your brain is thinking about. It's giving kind of that almost human touch to it, if you want to call it that. It's giving emotions to the different aspects and to what's happening around you. There's a few key ones we have to look at though. We have the amygdala. Now the amygdala, anger, danger, and fear. Kind of good things to keep aware of. Kind of get your body ready to react in the case. Anger, danger, and fear. The amygdala. We have the cingulate gyrus. Cingulate gyrus is more resolving mental conflicts, helping to express emotions through gestures. Well, resolving mental conflict, what is that? That's the whole idea again of the angel and devil on your shoulder. It's the should I do it? Should I not do it? Should I do it? Should I not do it? That back and forth you feel. That's going to be your mental conflict. So this cingulate gyrus helps you try to resolve that, to figure out a solution past that mental conflict. And the hippocampus. The hippocampus is putting information into long-term memory storage. Things that you're going to remember more than a couple of days. Now, not everything is put into long-term memory storage. The hippocampus doesn't remember everything. Think of it this way. Do you know what you had for lunch 37 days ago? As long as you don't have the same thing every day? No, most people don't remember that unless it's a special day, or you have the same exact thing every single day. But more important life events, those are put into long-term memory, hippocampus. Now let's take a hypothetical. Let's say this hippocampus was damaged. What would the result be? Well, no new long-term memories. But would you still have your long-term memories from before? Sure. Those are already put into long-term storage. You just can't put any new memories into long-term storage. So if, for example, this hippocampus became damaged, anybody you knew before that event, you'll still know them. But anybody new that you meet after the event, if you don't see them for a couple days, you'll forget all about who they are. You'll be reintroduced to that same person again if you see them a week or 2 weeks later, because you can't make new long-term memories. So hippocampus, long-term memories. So if we look at the structures here, cingulate gyrus is going to be this kind of blue structure up top there. Kind of see it wrapping around a little bit. We then have the amygdala. It's just this piece right here. And we have the hippocampus kind of curling up around there. So 3 different parts of the limbic system that we're talking about. Is there more than that? Yes. But those are the 3 to kind of point out to kind of give you an idea of some of the parts and pieces of the limbic system. All right, so some more parts and pieces of the brain from the limbic system and emotions into controlling aspects. So the brain has a lot of complexities going on with it.